because I'm not changing. The Arrhenius acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions. So the hydrogen ions, meaning H plus, right? So Arrhenius said that if you start to increase H plus, then you have to have had an acid dissolved. So, you know, chemically, however he decided to do whatever he was doing, the hydrogen ions showed up. He said, okay, well, this must be an acid. Again, why he named it this way, who knows? He also said that a base, when dissolved in water, increases the concentration of hydroxide ions. And hydroxide ions are OH minus. So if you put a base into solution, then OH minus would show up. Bronsted and Lowry realized that this definition that Arrhenius had was good, but it did not cover everything, because Bronsted and Lowry realized that hydrogen ions cannot exist in your nonpolar organic solvents. Hydrogen ions are only in aqueous systems. So hydrogen ions, this definition didn't work for everybody. It worked for a lot of different acid-base stuff. It didn't work for everybody. So Bronsted and Lowry said, let's make it even more general. Still cover all our bases with Arrhenius, but make the statement a little differently. And now they came up with the idea of a proton donor or acceptor. And a proton donor is one that will give up AH plus, and a proton acceptor is something that will want to accept an H plus. Now, to talk a little bit about this in the grand scheme, let's take an acid that everybody's familiar with, right? HCl. Hydrochloric acid, main component of stomach acid. When hydrochloric acid is dissolved in water, an equilibrium type system occurs, and what we have is the donation of this proton to water. The reason why is what I'm going to try to get you to wrap your head around when we start talking about equilibrium constants. But HCl will donate a proton. So here we have an acid, and here we have a base. If that is the case, then the donation of a H plus to H2O will give us H3O positive. Again, you can't get rid of charge, right? Formal charge has to be there. So we end up with H3O plus. What are we left with?
Chloride.
Chloride ion, Cl minus. Okay, so this is the reaction that occurs. This is a generic acid-base reaction. I'm giving you an actual example. A lot of times you'll see this written HA plus water gives you H3O plus A minus. Same concept here. Same concept here. One thing that I must say from an energetic standpoint, from what is really happening, H plus does not exist for any extended period of time by itself. H plus, because it has one proton, no electrons, it is highly unstable by itself. H plus is immediately looking for a lone pair to associate itself with. Where's the lone pair? The lone pair is on the oxygen on water. If we look at oxygen, we see this H is losing its one electron it brought to the ball game to chloride Y. Goes back to your Gen Chem 1. Why is chloride able to take that electron?
Fills its octet.
It fulfills its octet, but it being able to take it says something about what?
It's got a
Periodic trend high electronegativity, right? High electronegativity, high electron affinity. It wants that electron. Hydrogen doesn't have enough positive charge in the nucleus to keep it there. So chloride says, yep, let me hold that. Then the hydrogen ends up over here, right? The hydrogen ends up, and we get formal charge on the oxygen due to the bonding situation. And then chloride, of course, has 8 electrons. Now that's what's happening from the Lewis structure perspective. This is one of the main reasons that we teach that in Gen Chem 1, to get you familiar and to show what's happening even if we were looking at the Lewis structures. So to define Bronsted-Lowry as a proton donor, we would define this as an acid because the H, specifically this H, we can put a little star right here. This H is this H, and we have donated. So an acid is always going to donate proton. Now, for that same reason, we can look at this exact same scenario and we can call water a base. And water is, in fact, a base in this scenario because it accepts that proton. And here is a more in-depth definition, or more in-depth explanation of the definition of Bronsted-Lowry acid. We have one removable acidic proton, in this case, that from the HCl, and a non-bonding pair of electrons to accept. Hence, we have 2 here on the water. They have done this exact same setup here, shown in Lewis reaction and in the space filling models. Realize that one thing that you must always achieve is balanced charge on both sides. Notice we have a neutral charge on the left and the right. Even though we have charged species on the right, they balance out to be 0. So water is that one of the few things that can be both. Water depends on the environment. It's like that wishy-washy friend that wants to act different depending on where y'all go. Water can be a base or an acid depending on what it is interacting with. In this case, we have ammonia and water, and we see water becomes the acid here because water will lose the proton to ammonia, which has a lone pair, become ammonium and hydroxide. So like ammonia solution that you clean with is going to be basic. Why? Because OH minus is produced in this case. Now, you might ask, okay, well, why is water an acid here, but it is in a base here? Why is it different in both places? I've said to you that it's because of what it's interacting with, but what dictates that? And it is the characteristic of the acidity of either thing that it is interacting with. If water is more acidic than the thing it's interacting with, it's going to donate a proton. If the thing it's interacting with is more acidic than water, it's going to pick up a proton. And this is where we, introduce this concept of conjugate acids and bases. And really, I'm going to write this as A, B, Ca, Cb. You have to be able to recognize and label conjugate acids and bases. In any given system, actually, not only do you have to recognize them, you have to also predict products and then label them. So I may give you just the reactants, tell you to give me the products of this reaction, or give me the products of what happens when the liquid ends up, when you dissolve the base or the acid in the liquid, and see what happens, and give me the conjugates. So, to use another example, since we've exhausted this one. Let's say that I gave you hydrocyanic acid. And I reacted that with water. Then our products in this case would be H3O plus, right? We're always going to have H3O plus if we have an acidic situation. H3O plus is always denoted and labeled as aqueous. And Cn minus, cyanide, also aqueous. Notice that my water is a liquid. My water is always going to be liquid when we have this in aqueous system, phase-wise. Your acid is always going to be considered aqueous. So we have balanced charge, we have our prediction of products, and we should be able to label acid, base, conjugate acid, conjugate base. Again, it doesn't matter which one you write first on the product side, as long as they're both there. As long as they're both there. Okay, base. Show an example of a base. Now, you looking at something, being able to determine whether it's an acid or a base is going to take just some practice and the use of contextual clues and the use of reference materials. What you're going to, there's one piece of reference material that you'll now get when we start into acid-base equilibrium. It's going to be a table of acid equilibrium constants. And those acid equilibrium constants are going to give you what you need to be able to look at two different things and say, okay, this is acid, this is a base. Generally speaking, when you see a nitrogen, almost always you're going to be bringing a lone pair with the nitrogen. Almost always, right? Alcohols, which is the OH group, when they are in a covalent molecule, are generally not acidic. They're not acidic more so than water. So this is a base. This is ammonia, alcohol. This is just a NH2OH. This is an alcohol with its nitrogen, but this nitrogen is in fact basic. And I say that because if you looked at the Lewis structure, right? If you looked at the Lewis structure of this compound, you would see this lone pair ready to accept, right? Ready to accept. So if this is in fact a base, then what is our product in this situation?
NH3OH positive.
NH3OH positive, right?
Plus OH negative.
Plus OH negative. Now realize that the H did not go behind the oxygen. The reason that we cannot put the H behind the oxygen is because the oxygen is not what's accepting that proton. So you got to make sure that you write it, because if you put the H over there, your law of conservation of mass is still balanced, but you don't have the right product. So again, these are aqueous. Now, the labeling of this has now changed our water from a base to an acid. Now we have a conjugate acid and a conjugate base. Notice we have created hydroxide. That's one definition, right? That was one of our definitions here. The Arrhenius definition says the creation of hydroxide, which we have done that. So Arrhenius wasn't too far off, but it's better to look at it from the perspective of what is being accepted or donated. And that's the word for water being able to do both things is amphiprotic. So here is a chart, and I never liked how this chart is set up. I never even used this chart, but the relative strength of acids and bases is important if an acid is considered strong. very important. You need to go ahead and just memorize these. Anything that I'm gonna consider strong acid is only 6 of them, I'm pretty sure. And you'll see that as like SA. HCl, HNO3, H2SO4, ClO4, and HI, and HBr. All right, so these 6 you're gonna always treat as strong. Now we'll get into what strong means here mathematically in a second. But generally speaking, these are the ones that you're gonna see associated with being strong. Which means that in solution, by definition, these mean that in solution, complete dissociation occurs. Complete meaning that we don't have this concept and idea of equilibrium like we did before, where there's some reactants and there's some products. The assumption here is that all of this turns into products. And I'm gonna show you that mathematically here in the context of equilibrium. If we want to talk about bases, these strong bases below water or below the H2O line are O2 minus, H minus, and CH3 minus. You won't see very many of these 3. You will see hydroxide. So hydroxide, any hydroxide, well, not any, most hydroxides are going to be considered strong bases. The ones that I always consider strong bases are going to be metal hydroxides that dissociate completely. Sodium hydroxide, potassium hydroxide, lithium hydroxide, strontium, and barium, I'm pretty sure, is the ones that are considered. Now somebody might ask, okay, why aren't the other alkali earth metals? And that is because they bind onto the OH stronger, and they're actually not very soluble or not as soluble. So you have to take those in consideration. What does that mean? That means that these are the 5-ish that are considered strong bases. Now, if we look at these from the definition of strong base, we also should notice that these are all ionic compounds. What do we know about ionic compounds in solution? Particularly these, most ionic compounds are going to be completely dissociated in water. They're completely soluble. So with that is the case, then the addition of an OH to a solution is going to create OH, and we still fall underneath our definition of bases. So the same definition applies to both of these. In solution, we expect complete dissociation. So if a strong acid or a strong base is dissociated, let's talk about this qualitatively. What does that mean? That means this. That means that if you have NaOH plus water, then you are going to have NaOH plus water. Now realizing that the OHs have switched. Let me do this and make this a little more clear. right? So our sodium hydroxide has dissolved in solution. The OH interaction with water, since OH is a strong base, is going to take this black proton here away from this water, leaving hydroxide behind. So you haven't necessarily done much different when you have dissolved OH, but realize that this OH that is originally introduced is going to take a proton from the water that you dissolved it in, which is going to leave you with a hydroxide ion and a water now that has not just one black proton, but two. So there is a reaction occurring. There is a reaction occurring. It's just for you to see both of them on both sides, right? It doesn't make much sense. Now, most of the time, you will see this written without the sodium. And the reason for that is because sodium, if you notice up at the top, none of your metal ions, your positive metal ions, are very basic. You know, they don't interact in the acid-base nature. So normally you see this written as such. You see OH minus plus H2O gives you H2O plus OH minus. Same concept, same balanced charge on both sides. The reason that this is considered strong is because it completely dissociates. So then, now let's see if you understand equilibrium. If this completely dissociates, then what do we expect for the KEQ for these reactions?
Do the same on forward and reverse.
No. Complete dissociation means what do you have the most of?
Your products are favored.
Products are favored. If I say complete dissociation, then what do we expect for KEQ?
To be reactant side.
To be
Greater than acid.
huge. Complete dissociation means that we have little to no reactant left. What does that mean? That means that our denominator is approaching zero. So as this approaches zero and this approaches some number, you realize that we have, in calculus terms, what we call that? What kind of relationships? Asymptotic relationship, right? You never get to zero, but you're constantly, increasingly getting towards it, but it's such a small amount. That's what happens when you're dealing with strong acids. Therefore, we do not have a KEQ for any strong acids or strong bases.
What if you mix a strong acid with a strong base?
We're going to get to that.
We can still have complete dissociation.
We're going to get to that. We'll talk about that. Strong acid, strong base mixing is the basis of titration. That's the basis of titration. But KEQ, if you have KEQ, if you looked at the KEQ of any strong relationship, any strong dissociation, it is approaching a number, right? We can't divide by zero. It's asymptotic. We assume, fairly enough, that we have complete dissociation. We assume that everything turns into products. So if we were in an ice table, if we were in a equilibrium situation, whatever concentration of acid was dissolved is what you expect the concentration of hydronium ion to be. And we'll go over those examples of that as well. So here is your strength, and that's where we just talked about. So whenever equilibrium is involved, see in this case, we have HCl, which is strong, so equilibrium is way, way greater than 1, huge. Now here at acetate is a base. Well, this is acetic acid, excuse me. So acetic acid and water creates hydronium and acetate. Acetic acid being vinegar. That's why vinegar has got that, to you, that taste, that kind of stingy taste. That is a characteristic of acids when you ingest them. So equilibrium favors the left side. Now, when we talk about the stronger acid and stronger base, I still have to show you numerically how we are able to rank those. And water does its own acid-base work. So water, I always like to use this example because it's very interesting. Once you learn acid base, it makes sense. But if I was to give you a glass of deionized water and ask you to describe to me pictorially what you expect to be in that water, and if I told you it's pure deionized water, most people are going to write in water, right? This is what we teach in the high school level, even through general chemistry and intro chemistry, but this is not what water would look like if it was pure water with nothing in it, right? It would actually look like more like this. And the reason is because water is constantly autoionizing, becoming an acid and a base, and exchangement of protons. There are some water molecules that are H2O, but the majority of them actually are somewhere in between OH minus and H3O plus at any given time. If you had a pure deionized solution of water, right? And if we look at the reaction, right, of water with itself, then we see this. And this is, just like any other reaction, an equilibrium system. It's an equilibrium system, right? So if this is in fact an equilibrium system, what is our KEQ? No, the expression. Give me the expression.
Concentration of OH.
Concentration OH minus. Over nothing, right? Over 1. So this is our KEQ for this specific reaction that's occurring in any water that you have. It's occurring in your water bottle right now. It's a little bit different because your water bottle is a buffer. We'll get to that because they put stuff in bottled water. But if you had pure water, then this is your KEQ. We specifically call this KW. Specifically, this is known as KW, and KW is OH minus times H3O plus concentration. Doesn't matter which one comes first. And this equals 1 times 10 to the negative 14, times 10 to the negative 14 at 25 degrees. So that's going to be the assumption for any time you have it at 25, you're going to use that value. You need to know this. It's on your paper. Now, it's very interesting, this number 14, and how this impacts acid base stuff. That number 14 is the reason for the pH scale. And that's why the pH scale goes from 0 to 14. It's because of this autoionization. And we call it the ion product constant. You'll just hear me refer to it as KW. But KW is very important because if you add or remove, if you add anything, acid or base, to water, you shift the amounts of each of these. And once you shift the amounts of each of these, this number will never change. Because as you shift one, the other, right? Law of conservation of matter. You cannot have a KW that is not this value when you're dealing at 25 degrees Celsius, regardless of what you add. KW is a constant. That's why, constant. Think about that. Constant, that means it's constant. Okay.
What's the W for water?
Yeah, W's for water, yeah. So it's equilibrium of water, essentially. Now, I'm going to give some example questions because this particular chapter is a chunk of information. But here they want to talk about the pH scale, and the pH scale should be familiar to everybody. We got 0 to 7 to 14. Okay, from 0 to 7 we consider that what? Describe that as being acidic, correct? At 7, we consider it neutral. And then above 7, basic. Okay, so these are the areas for each of these. If the solution is neutral, and I hate that they use this description. They should be using hydronium. If it is neutral, then it's H3O plus is equal to OH minus. And that's at, so this means your pH equals 7. Anybody remember the equation for pH? Negative log of hydronium. Should also be on your reference material, I think. I don't know. It might not be actually.
H plus instead.
So the reason that I say don't use the H plus is because you won't see me write H plus on anything. It's always going to be H3O plus. Also, expectation is when you're writing out any of your acid-base reactions to use H3O plus, because H plus literally doesn't exist. That's just a shortcut that the books write for you. But from a content perspective, I don't like using it. Again, for a solution to be acidic, then you have to have H3O larger than OH minus. And we have a pH that has to be less than 7. Then to be basic, we need an H3O plus that is less than OH minus, and therefore we need a pH that's greater than 7. All of these pHs are a function of this calculation, not a function of Kw. If you notice down here at the bottom, they've shown you a strong acid, a strong base, and water, and notice that the Kw for all of these, if we were in fact at 25 degrees Celsius, is the same for each. Kw doesn't change. What does change is OH and H3O plus, and as those shift, the other one shifts up or down. They are intrinsically related when we're talking about water. So with that being said, let's look at 2 examples. Prediction of products, determination of conjugate acid, conjugate base, and then determination of what you think the pH is going to be. So you should be able to predict both of these products correctly. Label them all as acid, base, conjugate acid, or conjugate base. You should be able to write the equilibrium expression, because we already learned that, and you should be able to determine whether the solution after dissolution is going to be acidic, basic, or neutral. Back, you know. I don't know why this thing up here don't work. It's so stupid. All right, we should have this nailed down. This, we should be able to label this as a base off the WAM. The reason that nitrogen, almost always, your nitrogen is going to be the case. Nitric acid, notice where the H is. The H is in front, but nitric acid is probably the only other one that you're going to see from an acidic side. Now, therefore, that means that our base needs to be H2NNH plus hydroxide aqueous. And again, your phases are important. I will be taking off if the phases are not there and they are not written correctly. All right, our conjugate acid is now here and our conjugate base is there. Sorry, CACB. If we had to write the equilibrium expression for this particular situation, then we end up with all over. Again, water does not involve itself here because it is a pure liquid. Does not involve itself. HBRO. Turns into hyperbromite. HBRO is an acid. Water is the base. Hyperbromite is the conjugate base, and then hydronium is the conjugate acid, and we see that KEQ here is equal to H3O plus. Again, the order doesn't matter, just make sure it's written correctly. All over HBRO. Again, the equilibrium stuff is no different than what we've already learned. We're just utilizing some compounds that we are now designating as acid or bases. Any questions about this portion? The last thing that I asked you to do will explain, but is there anything right here that is not clear or confusing?
Are we able to determine that HBRO is an acid?
Generally speaking, outside of the way that I have kind of written this one, H in front means an acid. That is almost always, that's going to be the case. If you notice, even with that last example that I wrote, you notice it was NH2OH. So this should have been better written as NHNH or N2H2. So generally speaking, you're going to notice that. The only N that you're going to see associated with, whenever you see nitrogen, almost always is going to be a base. The only N you're going to ever see associated with an acid is nitrate. And HNO3, HNO2, HNO. Those are normally the only ones that you're ever going to see. So this is a base. This is an acid. The H being in front, but you just kind of have to know your acids. You should be able to look at them and kind of tell. If you also thought about this idea of the Lewis structure of this, right, you could convince yourself as well. So if you looked at the Lewis structure of proton wants to be donated. The reason, because oxygen, highly electronegative, wants that one electron, right? If you looked at the NH, lone pair, nitrogen less electronegative than oxygen. Again, but that's kind of partially the reason for the hydrogen bonding. Remember, all of that stuff we talked about is related, but it's a little bit more like that. Now, why, then the question becomes, why is this not a base? Because these lone pairs are here. And that has to do with oxygen preferring to be O negative, which is what is happening once this goes away. then you end up with the conjugate base. NH would rather hold that positive charge, more so. But again, a lot of that has to do with the periodic trends, all the old stuff. But normally you're going to be able to see that as a function of how it's written, or the name, if you get the name with it as well. pH of this first one, we expect the pH to be
Less than 7?
first one
Greater than 7?
greater than 7. OH minus. When you got OH minus around, you expect basicity. And here, we expect the pH to be less than 7. Again, pH is a function of hydronium concentration only. The hydroxide concentration impacts pH, but we can't calculate it from here. We'll talk about pH calculations here in a little bit. But that was a good example that kind of incorporated everything up until this point. And right on time. I didn't even remember what was next. pH, negative log of hydronium concentration. Mathematically speaking, whenever we are trying to solve for pH, we have to use hydronium. But our equation, and I'm about to erase these strong acids and strong bases. But when we are using this equation, we need to realize that we also have the ability to use Kw. So we have pH, we also need to remember that Kw equals H3O plus OH minus. And this equals 1 times 10 to the negative 14 at room temp. So pH calculations and how to do them. Very basically, I need to run through the basic math first. So with your calculator, if I told you that the pH, question, we'll go part A. Question A tells you that the hydronium concentration is equal to 0.00035 molar. And I ask you to solve for the pH. This is a very straightforward plug and chug. You should have recognized this you should have recognized this equation. You should have already done a math problem like this. But I promise you, people are gonna jack this up when pressure is on. So might as well practice the simple stuff early. That's why you shoot free throws.
So it's an acid.
Well, the pH, if you do negative log 0.00035, we see that the pH ends up being 3.46. Remember, the pH is only reported to 2 digits after the decimal. All right, so being that the pH is 3.46,
How'd you get, I got 3.66.
No, I got 3.1.
yeah, you entered it wrong. Negative log 0.00035. Make sure you got 3 zeros.
Yeah, but
3.5.
I got 3.66.
I don't know what's wrong with you. I don't know, you didn't put something funny. 3.46. 3.46. Now, this pH being less than 7, we can describe this as being acidic. Right? We can describe this as being acidic.
I'll put minus sign instead.
Okay, yeah, you can't put the minus. Yeah. So we describe this as being acidic. This is a calculation that you will have to do in a problem, but it won't be the problem itself, right? You're gonna have to do this calculation once you get your K and you do your ice table and you find concentration of hydronium, then you're gonna have to tell me pH. Okay, now let's look at the opposite direction. Let's look at me telling you that the pH is equal to 10.30. What is H3O plus? A little bit different now. First off, we can already describe this as being what? Basic, right. We can already describe this as being basic because we have enough information just off the pH alone, above 7. H3O plus, however, we need to do some rearrangement mathematically. The log is not, since log is a function, we have to do the anti-function of log. So to find H3O plus, we have to do base 10 raised to the negative pH. That's going to be something that people are going to mess up. pH, again, stands for negative log. The inverse function of negative log is second log, which is 10 raised to the x. The negative sign must accompany the pH. Negative sign must accompany the pH. And this number should be extremely small. And why? 5.0 times 10 to the negative 11. Okay, very small, right? Some to 10 to the negative 11 is like it doesn't even exist. It's there, but it barely exists. Now, does this number make sense to us based on what we know? Yeah. Right. It makes sense to us because of what? What should tell us that this number makes sense?
It's smaller than the K value of W.
Yeah, well, no, it's not smaller than KW. KW is not 10 to the negative 14. We should expect this number to be small because of what other piece of information?
Because pH is over 7.
Right. Because the pH is basic, we don't expect to see little to any hydronium around. Now, let's take a look and see, can we calculate the hydroxide concentration? Hydroxide concentration from here. Let's say I also wanted OH minus. Now we moving and shaking in the math department. I have to give you another relationship. I don't have to, but I like to give this relationship. pH plus POH is equal to 14. Okay? The reason for that, again, those of you all that are math savvy should recognize that if at pH 7 you have neutrality and you have equal amounts of this, then your concentration at 25 degrees Celsius of each of these has to be what? 1 times 10 to the negative 7 for both. If anybody is math savvy enough to know what the log function actually does, negative log, the log function just pulls this exponent down into the front, right? And since this is a 1, this ends up, the P, the negative log of H3O plus, that's neutral, is equal to positive 7, and the negative log of the OH in a neutral solution is positive 7, and that's where this comes from. But you don't have to go through this all derivation, you just got to remember this. If you remember this relationship, then you can solve for OH minus by determining POH. And POH has to be what? 3.70. Therefore, we can do the exact same thing here. OH minus equals 10 raised to the negative POH. And then we can mathematically determine that. second log, negative 3.7. So pretty much 2 times 10 to the negative 4. Way larger than our hydronium. And that's what we should expect, right? We should expect to have an amount of hydroxide that is much larger than hydronium due to the pH and due to the fact that this is basic. Now, if you multiply this number and this number together, you should get Kw. Five times 10 to the negative 11.
Exactly.
Exactly. Right. So this is the idea that Kw is a constant. Doesn't matter what you have more or less of, these two values should always get you back to Kw. Now, the third way to solve for this, there's one more way. If you were to be asked this kind of question, you could solve for OH minus as well by using Kw instead of going to POH. You could take this number and divide Kw by Kw over H3O plus because of this relationship. And this has to equal the same thing. 10 to the negative 14 over 5 times 10 to the negative 11 gives you hydroxide. Should give you this number. So being able to calculate pH is going to be important. And I just went through this, right? Taking the log of each side gives you 14 as a total. Here's your strong acids. So they added HClO3 minus. I don't normally see that one. All right, so your strong acids and strong bases are important. Now, I had somebody ask about what happens if you mix them together. Well, you tell me. I'm gonna write up here a reaction that does the mixture of a strong and a strong, right? And then we'll talk ourselves through it. We have sodium hydroxide plus hydrochloric acid now what was said about both of these? One, we can describe them both as being strong. Therefore, by definition, complete dissociation. So if that is the case, then you don't have to write it like this, but I'm going to write it like this to show you. If that is the case, then what does that mean that this really looks like?
Na plus HCl.
Now, what did I say about this particular species that is what? Right, it doesn't exist because why? Because it's going to do what? It's going to attach itself to something very, very fast. Well, chloride is happy. Octet fulfilled, stay away from me. Sodium, happy. Octet fulfilled, stay away from me. Hydroxide and H plus are going to find each other immediately. So you're going to have water. So you make water. And
Sodium chloride.
sodium chloride. So reaction of a strong and a strong together is going to create a conjugate and a conjugate, just like before. The only difference when you're creating strong is that both of your conjugates are technically neutral, right? Neither one of your conjugates have acidic or basic characteristics necessary, because you're creating a water, and that water is involved with sodium and chloride, which are not acidic or basic because of electronic structure, right? Octet, they don't want to interact with anything. That's the reason why they don't. But we're gonna have to wrap our heads around certain conjugates that do have acidic or basic qualities. But when we're talking about strong, if we add those together, we're gonna make water and a salt. This is called what kind of reaction? You should remember from Gen Chem 1. The name of this is called acid-base, is more commonly known as neutralization reaction. Why? Because you had an acidic thing, a basic thing, but you end up over here with a neutral situation. If these number of moles are equal, then you have 0 acid left, 0 base left. Water and salt is going to be neutral. So you can neutralize them.
Would you keep NaCl as aqueous?
Yeah, you get NaCl as aqueous, yeah. Na plus and Cl minus are both going to be floating around on their own, right? They're going to still be in solution like this, but they're going to be interacting with each other because of charge. So, better written, what would be expected of you is to write H2O liquid plus NaCl aqueous. Another thing is that if complete dissociation occurs, then this is another situation where we do not worry about the reverse reaction. We do not worry about the other direction because we have a KEQ that lies way far to the right, way over here. So we're never worried about reversibility when we're doing strong and strong. Never worried about that. But we do have to worry about that when we're doing strong and weak. Strong and weak. So let's do an example, try to incorporate everything, and then we'll take a quick break and then switch gears and move into Ka and Kb, which is when it gets real fun. We'll do 2 of them. You do this, you have absorbed some knowledge today.